Hey there, folks. In this video, we are going to go through a few of the practice questions from our universal gravitation handout. And so this is page 7 on that handout. And question 1 through 2, here's the scenario. An asteroid is very, very far away from the moon and moves with negligible speed. The moon has no atmosphere, so we will not consider air resistance. We're going to define two moments. Moment A, the asteroid is very, very far from the moon, and any other planet or moon is moving at a negligible speed. So in other words, the distance between the two objects is infinitely far, and the speed v is 0. Moment B here, the asteroid is just about to crash into the surface of the moon. So we're going to fill out an energy giver-receiver diagram for this interaction. We're going to fill out an energy bar chart to show the energy in the asteroid-moon system at moments A and B. We'll note that the bar charts below allow for positive and negative values, and the horizontal line at the center of each bar chart designates 0 energy. So let's go ahead and talk about this. In this, we have an energy giver and an energy receiver. The energy giver is the moon's gravitational field, and that field is giving energy to the asteroid. That's what's speeding it up. So in other words, we have a negative change in gravitational potential energy and a positive gain in kinetic energy. So that's going to start us off. So in other words, we can write our conservation of energy equation as the negative change in gravitational potential energy equals the positive gain in kinetic energy there. Cool. And the interaction type here is a gravitational interaction. Gravitational interaction between an object with mass and a gravitational field. So that's one way to model this. An equivalent way to model this is with bar graphs, but we have an energy equation that can take on negative values now, and so it's going to be a little bit different than what maybe we're used to. So things that are in this system are going to be the asteroid and the moon's G-field. Because those are the two things that are interacting. Those are the giver and receivers of energy in this situation. So energy at moment A. We have no chemical energy. And we're going to put 0 in the middle now because we can have negative and positive values. So no chemical energy, no elastic thing is stretched or compressed. We are infinitely far away, and our 0 reference level for infinitely far away, our 0 reference level is set to be infinitely far away. So we have no gravitational energy at moment A because we are infinitely far away, and we said we're going to define that to be 0 energy. The asteroid is not moving, so we have no kinetic energy and no air resistance, so no thermal energy. So we start off with 0 energy at moment A. 0 relative to all of our references. Now, the gravitational energy is at its maximum value at moment A because infinitely far away means we are as high above the surface of the moon as we possibly can be. That's the most energy. And so the change in energy is going to be a drop. We also saw that when we put a negative sign in our giver and receiver diagram. And so we start at 0 and the gravitational energy goes down. That means we have a negative value because we have less energy than we had at moment A. And we said just by our choice and reference that we had 0 at moment A. So now we have a negative amount. But the total energy must be the same between moment A and moment B. We had a total of 0 energy here, so we must have a total of 0 energy here. That means the negative gravitational energy must be matched by an equal gain in positive kinetic energy. And so overall, this equation looks like 0 equals, we have a gravitational potential energy still at B plus a kinetic energy at B. And we're just going to keep in mind that these are all pluses here, but the first number, this GPE, is a negative number. So we have a negative number plus a positive number and that negative plus a positive will give us 0 in the end. There we go. So there's our model. That's how we use the fact that we have negative gravitational energies when we are closer than infinitely far away. Negative in this case just meaning less than the maximum possible, and we set the maximum possible to be 0. All right, so there's our bar chart. Let's do the same thing. Now, in this scenario, let's read it. Question 3 and 4. An asteroid is very, very far from the moon, and it's moving with a non-negligible speed toward the moon. So we got 2 moments. Moment A is the asteroid is very, very far from the moon, so the distance is still infinitely far away, but we are moving toward it. Moment B, the asteroid is just about to crash into the surface of the moon. So let's model that. We have the giver-receiver diagram looks something like, give me a second to erase some things. Blue mark pen's back, great. Okay, fill out the energy bar chart. So what does it look like? Well, we still have the moon's gravitational field giving energy to the asteroid. The asteroid started with some kinetic energy, but it's still gaining kinetic energy. That's what it's doing. There is a positive delta on that kinetic energy. It starts with a value, that value goes up. And the moon's gravitational field is giving energy from the gravitational potential energy storage account. It's still a gravitational interaction. And our conservation of energy equation then looks like negative delta GPE equals positive delta KE. Fantastic. What does the bar graph look like here? The giver and receivers are the same, so our system is the same. The system is still the asteroid and the moon's gravitational field. There we go. Energy at moment A. No chemical energy, nothing stretched or compressed. The asteroid is infinitely far away, so by our choice and reference, the energy is 0. But it has some kinetic energy now. There is some kinetic energy where there wasn't before. And then no air resistance or anything, no thermal energy. All right, moment B, let's think about that. Still no chemical energy, still no elastic energy. But the asteroid's going to travel the same distance to the moon, so it's still going to be a decrease in 2 bars of gravitational energy. Same as before. We're going to drop from our reference of 0 down to a lower energy because we have less energy than that start. We are closer to the planet. We are less high off the surface. But we started with a bar of kinetic energy, and that means that, maybe I should have made these bar graphs bigger because we're actually going to need 3 blocks of kinetic energy. And it's no thermal energy, no air resistance. The way to think about this is we have 1 block over here, and that has to be equal to the -2 plus 3 blocks over here. So that's the way to think about the negative energy when we're bar graphing here. As an equation, we can think about this as the kinetic energy at moment A, so we do start with some kinetic energy, is equal to the gravitational potential energy at moment B plus the kinetic energy at moment B. So here is how you would model these situations with our new idea that we have gravitational energies reference being 0 at infinity, and then it drops from there as you get closer. That's the main idea. I do want to add an extension to this real quick. I want to say, what would the next step look like if I were trying to solve for a given value? The next step here would be to plug in mathematical models. And so the math model for 0 is 0. The math model for gravitational potential energy, sorry about that. Math model for gravitational potential energy is negative universal gravitation constant, mass of big object, mass of small object, divided by the center-to-center distance between them, plus the kinetic energy is 1/2. This is the asteroid that's moving, the smaller object, little m, times speed squared. And little m does matter there because we also have a big M, and that's not the one we care about. You care about the little m, the asteroid's motion, and this is the speed at B, so I'll put a subscript there. And just so we're extra clear, This GPE at B is this equation with the negative sign. It's a negative value based on our choice and reference. And this KE here is this half mv squared here. So that's where all of that comes from. And then you could do some rearranging, isolating your find, plugging in numbers, etc., etc., etc. Similarly, in the next one, let me get rid of that highlighter. If we move on to the next one and scroll down, what would our equation look like? It would look like the kinetic energy at A is 1/2 the mass of the moving object, the asteroid, times the speed that that object has at A squared. And that's equal to negative big G, big M, little m over distance plus 1/2 the mass of the asteroid times the speed at B squared. And to be clear, this KE at A is half m times the speed at A squared. This GPE at B is negative G big M little m over distance squared. And this KE at B is this half m V at B squared. The last thing I'll say before I sign off here is that we are not going to use the equation GPE equals mgh when we're dealing with situations that involve outer space. That equation only applies if G, the gravitational field, is constant. But since we are in a changing gravitational field, we must use this equation for gravitational energy. Cool. So that's how you set up situations using our new mathematical model for gravitational energy.